Hello everyone, my name is Luan. My topic today is extended narrowband weighted multi-flip for two-phase liquid simulation. Here's the outline of my topics. First, I will give you an introduction of my topic. In our daily life, liquid-gas interaction can produce many interesting phenomena, such as droplet, bubbles, and the clogging effects of water pouring. And for the sake of computational efficiency, there are so many methods only simulated one-phase kind of fluid. So in order to simulate two-phase phenomenon, Bob and Gleason proposed the MultiFLIP method. However, MultiFLIP have two challenges. Gas and liquid particles are required to fill all the volumes. And the second is that MultiFLIP uses same weight for both gas and liquid when blending the velocity, and this may cause some abnormal phenomena. So in order to address the two challenges of MultiFLIP, we present a novel weighted velocity transform method, and also we apply the transition function of extend narrowband method to our simulation. And finally, we propose a surface tracking function based on the transition function. And then I will give you some related work. First, our method is based on the implicit incompressible Navier-Stokes equation. And unlike the one-phase fluid simulation, which only involve one kind of fluid, our method involves two kinds of fluid, so we use a variable density when we simulate the fluid. And in 1999, Joe Stem introduced the stable fluid algorithm. He described the fluid attributes on grid. And here's the basic algorithm for stable fluid. It involves 4 steps. The first is the advection of fluid field and the velocity field. And then is the external force handling, and also there is a projection step. And in order to keep the details of the liquid, Drew and Gleason introduced the flip method. Since the advection method introduced by Joe Stem may suffer from numerical diffusion, the main idea of flip is to represent the fluid and advect the velocity by particles. And this is the narrowband method. This kind of method uses just a few of particles to represent the fluid. And however, the flip is not suitable for two-phase fluid simulation. So Bob and Gleason introduced the MultiFLIP method to handle two-phase fluid simulation. And this method uses two kinds of particles to describe the two-phase fluid. And just as the narrowband method I introduced before, narrowband MultiFLIP use only 2 bands of particles to track the interface of liquid and gas. And then is our method. We divide our method into 2 parts. The first one is the weighted velocity coupling, and the second one is the extended narrowband method. MultiFLIP use respective velocity fields for gas and liquid. Before projection step, MultiFLIP need to couple these 2 velocity fields. However, MultiFLIP use the same weight for gas and liquid, and leading to some unwanted influence on fluid. And our method introduced the max of particle to our system, so we can measure the momentum and mass of the degree by interpolation, the momentum and mass of particle to the grid cell. So finally, we can update the grid velocity by dividing the momentum by mass on the grid cell. And here's the comparison of the MultiFLIP and our method. The left one is the result of MultiFLIP, and the right one is our method. And you can see that our method can successfully reproduce the scenario that the splashes of water droplet form a crown shape on the surface. However, MultiFLIP may restrain the motion of liquid, and leading to the liquid being greatly influenced by the gas. And then is the extended narrowband method. And the basic idea of the extended narrowband method is that particles are only generated in the area where detailed phenomena happens. So in order to achieve this goal, the first challenge is how to reconstruct the surface by fewer particles. Here are the such steps of surface reconstruction. And after adapting the particles and level set is a function to measure the interface of gas and liquid. After advection, we can construct a particle-based surface and a grid-based surface. And finally, we combine these 2 surfaces together with the transition function. And the transition function is the key value to switch between particle-based surface and grid-based surface. And here is the steps of the computation of transition function. The value of transition function is the value of transition function depends on the heat function and the heat of particles. And after obtaining the transition function, we can sample the gas and the gas and liquid particles. And in each step, we would cool down the heat of particles, and a particles is deleted from the system if its heat is less than 0. And also, we will create particles for the grid cell where the transition function is greater than 0. And these are the main idea of our paper. And then I will show you the result of our experiment. We compare our method with the narrowband MultiFLIP. The MBW MultiFLIP and EXMB MultiFLIP are our methods. The MBW MultiFLIP is the method with only the weighted velocity coupling method, and the EXMBW MultiFLIP with the both method I just introduced. And you can see that our method can reduce the particles, but however, our method just enhanced slightly in the runtime. And here comes the concurrent and future work. You can see that our method with weighted velocity transform from particle to grid can reduce the unwanted influence on fluid, and also our method with use the transition function can track the interface. And however, although our method can reduce the unwanted influence, there are still some liquid particles getting carried by the air near the interface. So in future work, we would like to use some more robust velocity transfer methods. And here's them how this experiment. The demo is to test whether our method can produce the same tension as narrowband MultiFLIP does. And you can see that the narrowband MultiFLIP cannot form a cloud on the surface. And in this experiment, you can see the narrowband MultiFLIP may cause unwanted influence on the liquid. That's all. Thank you.